Now we will look at the second question of the quantum mechanics chapter. Problem 3.2. Expand an arbitrary wave function over the eigenfunctions of the operator to prove equation 3.31. And I have written down the equation 3.31 over here from the book. This says expectation value of an operator O is given by integral of psi star O psi integrated over the volume entire space d cube r. So this is the equation that we want to prove. Let us now look at how we will prove this. And for that, let me provide you with context of this problem. So over here, the operator is O. So O, which is, and the operator notation is denoted by this hat or cap or over the alphabet. So O is the operator. It's an operator, and an operator represents measurement. Operators represent measurement of any physical property, of any physical observable property. And let us also write down the eigenvalue equation for this operator O. So if an operator O acts on an eigenfunction psi I, then it will give the observable value eigenvalue OI and times psi I. So this psi I is the eigenfunction, and OI is the eigenvalue. This means that if you measure the property denoted by the operator O onto a state given by psi I, which is an eigenfunction of the operator, then the result that you will measure, the output of the measurement will be OI, this small OI. And here notice that in the eigenvalue, I have not written that hat over this eigenvalue. So that's how you distinguish the eigenvalue from the operator. Operator is denoted by a hat over the letter, and eigenvalues do not have that hat over it. So this is the eigenvalue equation, and it basically means it denotes the measurement operator onto any given state and the measurable value. Now, any arbitrary state can actually be written as a superposition of the eigenfunctions. So if I have any arbitrary state, psi can be written down as a superposition of the eigenfunctions psi I. So Ci is the coefficient of superposition, and these are complex numbers. So Ci in general is a complex coefficient. Now let us look at what measurement values we will get. So here let's say I have the input state, then the measurement, the measurement operator, and then I will have the output, the value, and then the output state as well. So my measurement is, let us say, some apparatus. I have some apparatus and I want to measure some property which is denoted by this measurement operator O. And if I have an input state psi I and I send this into my measurement apparatus, then the output that I will get will be OI, and the output state will remain the same, psi I. So that means if I send in psi 1, so let's say if I send in psi 1 into this measurement operator, let me copy paste this again, or let me first, sorry about that, let me just move everything a little bit up. I'll just shift everything up so that I get some space below. So if I send in the state, let's say psi 1, into this measurement apparatus of mine, then in this case the output will be O1 and output state will be psi 1. So this output over here is the measurement value that you will get. So if I want to make some measurement, the output will be some measurement value. And corresponding to that measurement value, the state, the wave function will be given by this output state. So this is when we send in states in the eigenfunction. So psi 1 will remain psi 1 and give you the output value O1. If I send in psi 2 into this, I will get O2 and same state psi 2. So if I send in eigenfunctions, the state will remain unchanged. Now what happens if I send in the superposition state, this arbitrary state over here? That is interesting. So let us look at it. So if I send in this arbitrary superposition state into my apparatus, so I will send in this superposition state into my measurement apparatus. Now this will actually sometimes give me the measurement value O1 with the output state psi 1 with a probability. This will be with the probability given by mod C1 squared. Then other times I will get the value O2 and the state will be psi 2. This will be with probability mod psi 2 squared. Sorry, mod C2 squared. Then sometimes I will get O3 with the state psi 3 and probability mod C3 squared. And so on and so forth. And this is what is known as the wave function collapse. This is what is known as the wave function collapse. And why? Because you sent in an input arbitrary state which was in a superposition of all these eigenfunctions. And when you make a measurement on this superposition state, you will get at times the value O1 with the state psi 1, at times the value, let's say O3, at times you will get O10, at times you will get O2, and so on and so forth, depending on how many eigenfunctions are there in this superposition. So let's say I want to make a measurement. Once I get O1, another time I will get O3, another time I will get O2, and so on and so forth. And the probability of getting these measurement output values is governed by these complex coefficient. So mod of the coefficient squared is the probability with which these particular output values will be observed. Now, the average value, if you want to know the average value that we will observe, so average value of our measurement, which is also known as expectation value of our measurement, this will be simply a weighted sum. So a weighted sum of all of these output values, and the weights are these probabilities, which is the mod of the coefficient squared, and these are the values. So weighted sum will be the average value, and this is what is the average value or the expectation value. So this right here is my expectation value, the definition of expectation value. It is denoted by this angular brackets. So the operator inside angular brackets, that denotes expectation value. Now we need to show that this expectation value is given by this integral representation. So let us look at that now. So let us start with the definition. So we have the definition of the expectation value. So this is from here we see that the weighted average is the expectation value, and this is what we denote as within the angular brackets as the expectation value. Now let us look at the integral representation. So let us look at this psi star O cap psi integrated over entire space. And since psi is this arbitrary superposition state, let us use that notation. Now the integral will go inside, summations will come outside. And now we will make use of this eigenvalue equation over here. So O cap psi m will be OM psi m by the eigenvalue equation. This is simply by the eigenvalue equation. And OM is just a number, it's a measurement value. We can take it outside the integral. And this, if you recognize, is the orthonormality condition from our previous question. So if we look at the orthonormality condition from the previous question, where is it? Here is the orthonormality condition from our previous problem, and this is what we will make use of now. So it basically means if you have psi n star, psi n prime, that is two different indices, and one of them is complex conjugated, integrated over the entire space, you get a Kronecker delta function, which means the value is 1 whenever these two indices are same, and the value is 0 whenever the indices are different. So using this orthonormality condition over here, we will come to the following expression. So this is a Kronecker delta function, delta nm, and this comes from the orthonormality condition. Now delta, because of this Kronecker delta function, we will get rid of one of the summation, because delta nm is equal only when is equal to 1 only when n equals m and it is 0 otherwise. So using that, we will get the summation over n Cn star. Now because n equals n, so this will be Cn and this will be On because n equals m, and this is nothing but summation over n mod Cn squared On, and this was what we had as the average value. So this is our expectation value. So this is what we have proved. So finally we can write down our result, that the expectation value can be given by psi star O psi integrated over the entire volume. And this, if you see, is actually the same as the weighted average if you write it down in the superposition state. So this is our final result. Oh, sorry, I should make it a proper rectangle. There you go. So this completes problem 2, where we looked at how to denote the expectation value of any measurement operator. An expectation value basically means the average value of the measurement output. So whenever you perform any measurement, you will get some measurement output values, some numbers, and the average value of all those measurements is the expectation value. So you will perform measurements many number of times, and the average of all those values is given by the expectation value.